Today we will see the available energy, what's the expression for available energy in an open system, and that we will consider. Basically we will derive an expression for available energy following the steps similar to the ones we followed for arriving at expression of available energy of a closed system. I don't have to tell you about the difference between closed and open system. For example, let's say example of a turbine where steam is flowing through the turbine. It flows through the turbine, and while it flows it expands and you get work. So it's a when you say open system, turbine is an open system, then there is the process. It is a flow process. Okay, the working substance passes through the control volume. So you can consider a concrete example of a compressor or a turbine. There could be other examples also. But a most general expression we will derive for finding out available energy. So let's say that this is some device. It could be any device. Let's say that there is some fluid entering here, fluid leaving out from this. There is shaft, that means indicating that there is work output. Okay, and let's consider that all of this is our system, or this device is placed in control volume. This is section 1, this is section 2. We will consider the flow to be steady. Remember the definition of steady flow. So the flow is steady, and we'll also consider that there is some flow of heat at certain instance. We will consider the flow of heat is dQ. It could be kilojoules per kg or kilojoule per second, whatever, but we'll say dQ. And let's say at that instant the work output is dW, and let's say the fluid is entering here and passing out here, and so the fluid which is entering here will have all kinds of energies. It will have internal energy, there is flow work associated with it, there is kinetic energy, there is potential energy. If you see the height, elevation from section 1 and section 2, there is elevation difference, so that means there is potential energy difference, which also will be available as work, right? So basically you will consider all kinds of energies here, and at any instance when there is heat transfer is dQ, work transfer is dW, the energy difference at section 1 and 2, let's say it is dE. We can say dE12 or dE. That means there is the energy here and energy here, the difference between them. So now we will apply the first law to this flow process, and in fact we have derived steady flow energy equation. All that you have to recollect that. So general expression we can say just following exactly what we did during last lecture. I can write this as dQ is equal to dE plus dW. Right? dQ is equal to dE plus dW. This is first law of thermodynamics. I have not said du because if it's a closed system which is a non-flow process, then there is no other term except internal energy. But here there will be internal energy, flow work, kinetic energy, potential energy, all those. So this is a general energy, so dE. Okay. So since we are considering heat flowing out, let's say minus dQ. So we can say dW is equal to minus dQ minus dE. So this is say first equation. Now we want to find out the maximum work, right? But remember there is also thermal potential, right? This entire system, right? It will have certain say temperature T at certain instance, and surrounding temperature is T0, and if we say temperature T is greater than T0, then it's because of this the heat is transferred. Okay, because of this temperature difference, there is heat is transferred to the surrounding. So we can say that this heat, again we can imagine that this, because we want to find out the maximum work that can be extracted from this system when the system reaches the dead state. Let's say dead state is surrounding temperature is T0. We have already done that. Okay, so surrounding temperature is T0. So we want to find out the maximum work. So what we do is we consider this heat which is transferred from T to T naught. We imagine that to be passed to a Carnot engine, and there is work output from the Carnot engine. So this expansion and flow which occurs in the system through the control volume, that is giving you this work. At the same time, this heat which is passing out, that is imagined to be given to Carnot engine, and that also will give you some work. So this Carnot work and this work will be added, and that would be the available energy, right, or maximum work. So I'm just putting this Carnot engine here, so for the sake of convenience. Okay, so this is dq. So let's say this is at certain instant when the temperature here is T2 of the working substance or the fluid, and there is this is dq. Then I'll say minus because this is giving. So this is dwc dq naught, and this is T naught. Recollect what we did last time. It's exactly on the similar lines. Okay. So I'll write expression for dwc. Now there is heat supplied dq to the Carnot engine. This is Carnot engine. Okay. So this is reversible engine. So dq is supplied to it. dq naught is rejected. Remaining is the work which you get. So I can write this as dwc is equal to dq, which is supplied, minus dq naught. Okay. dq minus dq naught. Please note that dq is the heat supply. dq is rejected by this, but it's given to Carnot engine, right? So as far as Carnot engine is positive. So dq minus dq naught. Okay. Now we can also, because this is a Carnot engine, we can also write that. Let me write this as 2, equation 2. We can write for Carnot engine minus dq by T is equal to dq naught by T naught, right? And from this I can say dq naught is equal to minus T naught into dq by T, minus T naught into dq by T. dq by T is ds, so it is minus T naught into ds. Okay, so this becomes your, let's say, third equation. And what I will do now here is I will substitute dq naught here. Okay, substitute the value of dq naught, expression for dq naught, in equation 2. So when we do that, let me do that. So this is minus T naught ds. Please note that dq naught is minus T naught ds. So I'm just writing this here as dq minus of minus T naught ds, right? So this is dq plus T naught ds. So let's say this was our fourth equation. Okay, so this is dwc and this is dw. That means I can say this as because of expansion, but I'm not saying, I can write this as E and F. That means this is the work which is because of expansion of the fluid and also because of flow of the fluid. Okay, so I'm writing this as EF, E for expansion, F for flow. And this is Carnot engine. So this is work output from Carnot engine. If you add them, then you will get the maximum work. So I'm adding 1 and 4. Please note, I'm adding 1 and 4. So dw max, adding 1 and 4. So this is minus dq minus de plus dq plus T naught ds. Okay, so this is our expression for maximum work, which is available energy. And now you can just try this out. So this is minus de plus T naught ds. Now this minus de, that means it is the change in energy at section 2 and section 1. The difference in energy at section 2 and section 1. So d will be, like you can say, E2 minus E1. So minus d will be E1 minus E2. So let's say that this is dw max. we integrate this, when we integrate this, we will have W max, maximum work, and this will be minus delta E. E will be transformed into delta E and plus T naught ds. Plus T naught ds. Okay. So I write this as W max, or it is available energy, is equal to, please note it is minus delta E. Delta E is E2 minus E1. That means energy at section 2 minus energy at section 1. So I write this as minus delta E will be E1 minus E2. Right? E1 minus E2. Okay? Plus E naught delta S. Okay? Again, this delta S is S2 minus S1. Right? So because here I am writing E1 minus E2, I would like to represent delta S, change in entropy also in a similar fashion as S1 minus S2. So all what I have to do is take minus sign. So I write E1 minus E2 and take minus out. So minus delta S, that will be S1 minus S2. Okay. So this is your expression for available energy. Okay. This is your expression for available energy. Now, please note that you can substitute 2 and this 2 by naught. That means the system has reached the dead state, right? So you can, of course, you can do that. So you can, instead of 2, we can say naught, that is 0. That means the final value is of the properties when the fluid has reached the dead state. Okay, fluid has reached the dead state. Please note that now here is something which you would like to compare it with earlier expression for closed system. What was the difference? The difference was, instead of E1 and E0, it was U1 minus U0. Okay. Now what is this E1? So E1 and, so basically E will stand for internal energy, flow work, right? Kinetic energy, V1 square by 2 plus Gz, potential energy. So all this put together is this E. Please note, all this put together is this E. So in the numerical, it's very simple for you. If you are asked to find out available energy, if you are given the properties at section 1, section 2, what you have to do? You have to consider the properties, right? At section 1 and section 2, find out the change in entropy, right? So you have to write this as S1 minus S0. That means you will find out delta S, but when you write it here is minus delta S. So S1 minus, that's done. Then E1 minus E0. That means again you will find out, add this, all this, internal energy, flow work, kinetic energy, potential energy at section 1 and at section 2. This minus this minus this. That's all. That is your available energy. Okay. But let me say that for a particular case, generally in the numericals, there might not be kinetic energy and potential energy terms might not be mentioned. They are to be neglected. Many times it's so. So what happens is the only terms are U plus PV. So what is U plus PV? It is enthalpy. Okay. When you neglect these kinetic energy, potential energy, then the only energy term which is left, we are left with, is enthalpy. So here this can be substituted by H1 minus H0 minus T0 S1 minus S0. Okay. So this is your expression for available energy in a process, for a flow process, okay, or an open system. When the system is open, there has to be flow process, and this will be your expression for maximum work that can be obtained when the system flows through a control volume and reaches the dead state. Okay, and this is available energy, or this is exergy